So now we have to come to the paper session. The first paper to be presented by Mr. Curtis Bradley, entitled Cognitive Tutors for Smart Studio Physics Classrooms. And Mr. Bradley is from the Petrol Institute, Dr. Bradley. So you have 15 minutes.
Okay.
Thank you.
I think I'll manage. I'll speak loudly enough, so it's okay. Yeah? If I'm moving around. Okay, yeah, maybe. So while we're getting hooked up, I'll just introduce myself. I'm Curtis Bradley. I've got colleagues at the PI. We call it Petroleum Institute PI, so I'll refer to that several times. And we've been working on this project now for about 3 years. I'm wired. So briefly, you should know where we're headed before we get on this little short trip together. First, I want to explain what studio physics is all about, and then talk about why cognitive tutors, what they are, what they mean to us anyway, and how we think it's going. Petroleum Institute, if you don't know, it's a rather new institute of higher education here in Abu Dhabi. About 13 years ago it started. Engineering university, fully accredited, and with the mission of graduating competent Emirati engineers for work in the energy sector in the country. We're sponsored by ADNOC, Abu Dhabi National Oil Company. So our focus is very, very clear with collaborations with many universities, but particularly Colorado School of Mines. With CSM, about 2.5 years ago, we started looking at ways of improving the way we deliver our physics education as well as other subjects. And we visited CSM, observed how they did studio physics. In particular, very impressed, and so we decided to do a pilot in the following semester. Why? What is studio physics and why is it interesting? Maybe many of you know, but it's worth laying the groundwork, I suppose. Traditional university education is designed for specific reasons, not necessarily pedagogical, economic, and others, okay? So beautiful, impressive arrangements have been made to teach large numbers of students at the same time. But for a physicist, for a scientist, the really interesting stuff is going on here, is in the interaction with the equipment, the talking about what you see, the observations, the conceptual development and testing of our ideas against reality. The problem is that that excitement that we feel as scientists for this kind of experience, and even the experiences going on in lecture, kind of what I'm trying to do here, doesn't work for everybody. And so too many of our students are frustrated by traditional education. There is a mismatch between the way we've designed the experience and the experience that most of our students have. So we at PI decided to adopt studio approach for physics. And what it is it's creating a new environment for learning that's student-centered, active learning. So it's got two basic goals. Of course, we want our students to learn more about physics and to do so in a collaborative way where they can apply what they know to solve problems. And to develop basic skills, but really more important than that is to generate good feeling, to get it so that students enjoy it more, so that they can focus more on what they're doing, so that they can stay with it and actually do the learning and be more successful. So we're looking at both of those things. performance. Does performance improve, but also do attitudes and emotional response improve? There are a lot of reasons why we're attracted to the studio physics, studio approach generally. There are research, decades-old research now, that was put together in this study about 7 years ago that showed there's lots of evidence that this kind of an approach is successful. Attendance goes up, conceptual learning goes up, student attitudes improve. Students, even after they've passed through your course, they are more successful in their subsequent courses. Okay, so there's transfer, which is very important. I'm not going to go through this. I guess what I want to show you is there's a bunch of things that we're looking for in adopting this new approach. We want students to be more critical. We want students to be able to make decisions with confidence. We want students to be able to document what they do and be true to our tradition of it being a measurement-based physical science course. So we're not giving up any ground on what we expect to be teaching in our course. To do so, however, we have had to make major changes in the way we deliver the course. We've reduced the amount of lecture and significantly increased the amount of time that students spend doing activities. So here in this example I show from last year, the bulk of the week is committed, is invested in student-centered activities where they're actually doing the work and then we are facilitating them with bookends of lecture, but active lectures. So we've changed the curriculum, we've changed how we spend our time, and we also had to change the environment, the physical environment, the architecture of the space in which the classes are taking place. So we got funding from to Career Refining. They were very generous and helped us to rebuild our laboratories. So this is what they look like now. They don't look like a traditional classroom or laboratory. Very comfortable space. Students are very at ease. So their emotional state is already improved once they just walk into the room. It's a small university. We don't have to have a class of 300 students. We have classes of 36. But we make good use of the space. These tables each have 9 students in groups of 3. Lots of room to do the kinds of high-quality experiments that we want to do for physics. The motivation for cognitive tutors is because we are changing the paradigm of what it means to come to class, for physics class anyway, is that we expect more from the students. We're expecting that they do more or that they are prepared before they come to class. So, and when they're in class, we expect them to do work in class, not just to watch us as instructors do the work. And so, because we are expecting more from them, we have to also support what they are doing in the class. So, instead of having lots of teachers walking around and making sure that they're making progress and getting a lot accomplished during the class, we've decided to do that with software. So we've developed our own set of cognitive tutors, programs, which help the students check their own progress as they work through the activities. These tutors give the students immediate, detailed, and adaptive feedback. So depending on the choices that they've made, the type of feedback will differ from one group to another. The workflow as students come into the classroom and are studying and working on the activities, we use a Blackboard as our learning management system. We've used others, but that's not the important thing. It's really what's in it, the curriculum that's in it. We've got instructions that the students follow, that they use as guidance, and they write down everything they do in their own notebooks. That's the medium that we use to evaluate and give feedback on their progress. This is an example where an activity about vectors. Here are the instructions, pretty simple as possible. to be to give the students as much opportunities to make decisions as possible. They use simulations in this activity, some very nice ones from a different university in Colorado. We expect students to write, not just play with their calculator or their devices, but writing and solving physics problems is very important. And until tablet technology catches up to the pencil and the pen on paper, we're going to continue with that. Maybe soon that we can replace it. And then here's the tutor. Tutors are very, very simple in appearance to the student, very complex under the hood. They're not anything as intelligent as what we just heard about from IBM. Okay, don't get me wrong. This is not the kind of leading, cutting, bleeding edge artificial intelligence that they're talking about. Our cognitive tutors are kind of stupid, but they're smart in the ways that they need to be smart to help the student in the classroom do the tasks and make good progress during the activities. So the students can check their progress. Here's another example where the students measure the acceleration due to gravity. We all learned what the acceleration due to gravity is, right? What is it? I heard it, 9.81. Wrong. Okay. Students are delighted to find out that in the UAE it's not 9.81, just like their textbook says. It's 9.79. And they measure it in our laboratory with high precision because we've given them the tools to do an excellent, high-quality experiment. And as you can see there on the screen, he's got the group has their tutor there so they can march through the activity, check their work. If they've made a mistake, they find out right away. They don't have to go through the whole activity and find out at the end, oh, our data is garbage because we were doing it wrong. Okay? We give them immediate, detailed feedback, step by step, so that they have the confidence to go on. Sprinkle in the activity, in the cognitive tutor, a lot of local references so that the students know that this is homegrown, this is made for them. It's not something that we just got off the shelf. The tutor asks questions of them so that it knows who it is that's using it so that we can keep track of which group did what. The different groups are personalized by different things. Like the boys tend to have a group that's named after a car, race car usually. The girls, okay, we use precious stones, diamonds and gems and things like that. Here's an example in that free fall experiment where the answer is 0. But the tutor won't accept this kind of a 0. Thank you. Why? What's wrong with it? Well, significant figures, okay? A measurement has an uncertainty. So 0 is not the same thing as 0.0. It's not the same thing as 0.0.0, you understand? 0.000. The student has to be careful and to report their values with correct precision in order for it to be a valid value. The results, in 2 minutes, are good, very positive. The first semester we offered it, it was just to a small section. It was perfect for doing the first pilot, the small section of girl students, hardworking students. We had good progress with them, well received by the students. The next semester we gave it to 2 sections. The next semester we did it for all of our sections at the same time. This, I think, is the most dramatic result that we've got. Students stopped withdrawing, or at least a lot fewer students withdraw from the course. They're sticking it to the end, okay? Whereas before we had a problem with students panicking in the middle of the semester and leaving the course. The other thing is that as students do finish the course, they're doing about as well as they did before. Well, that doesn't sound great, except that if we're keeping the students who were withdrawing and they're able on average to pass or to do as well as the other students, that's progress. The big happy result is the students love it, or at least a lot of them do. We gave a free response survey. We do this every semester now, and almost 80% of the students gave us positive feedback about the method and about the tutors. Only 10%, 11%, I guess, gave us critical feedback, and 10% said, well, the main thing I want to tell you is physics is stressful. Well, that's not too surprising, but I think we'd be doing something wrong if we didn't get some of those kinds of comments. So in conclusion, we're happy about this project. It's working. Cognitive tutors are doing what we want them to do to support studio physics. There's more that we can do. We can improve the tutors. We can make them smarter. We can develop tools for making it easier to make new tutors and to improve them. So there's lots to do, but it was a step in the right direction.
Thank you, Dr. Bradley. So we have one short question again. Yes.
Can we please hear more about the tutors? Are they within the Blackboard environment or outside of it? What did you use to put them together?
Good. I guess I meant to say that these are they're programmed in a spreadsheet, Excel, okay? They're standalone, but deployed to students. You can share them. It's just an Excel file, okay? A lot can be done with the tools that are within Excel. A lot of the working parts are macros that are in Visual Basic, okay? So to the student, they don't see all of that, but that inside there's all these little Visual Basic macro programs that allow it to have the kind of interactivity and the limited kind of intelligence that they do have. That's the kind of thing that it has taken some time to develop and some patience from the faculty. We don't have any programmers on staff. It's been done by teachers, by myself and a lab technician who has helped me. But we would like to develop it so that it's more easily shared and other people could make their own. The beauty of this thing, from my point of view, is that this kind of tutor is not something that you could ever expect to be store-bought, okay? Because it's customized to the local class, the realities of your class, the realities of your students. And you need tools to be able to create such things for your class. And we use textbook materials, textbook publisher materials as much as we can. But for experimental work, there really isn't anything that you could find.
How much would you say it takes to put one together in terms of time?
I think I made an estimate of that. It's several person workdays per tutor. And so it's a significant investment of time. E-tutoring? Yeah. Yes, I'm very much in favor with what we can do with the intelligence of the device and by communication and so on. At the same time, I'm extremely passionate about students getting together and working with real equipment and real phenomena and seeing it for themselves and making sense out of it in a classroom. Or it doesn't have to be a classroom, but in a real sense, not relying totally on simulated things. Okay, so it's...
Okay, thank you very much, Dr. Bradley.